So for most data warehouses, the workload or the type of work that is to be performed by the data warehouse server will be very different from what is called an OLTP or online transactional processing type workload. Most people are very familiar with OLTP workloads, and so by comparing and contrasting that with the data warehouse workload, I hope to increase the understanding that these two are actually fundamentally very different, even though sometimes the same or similar hardware can be used to manage these different workloads. So, to begin with OLTP systems, these are fundamentally seek-centric workloads and characterized by random reads and writes. One of the more popular metrics whenever you purchase hardware infrastructure to support this type of workload, one of the best advertised metrics around this in terms of performance is IOPS, or in and out operations per second. So what I mean by seek-centric is that usually most of the result sets from these type of queries are fairly small, in the tens or hundreds of rows range, and that you're seeking individual records or a small handful of records from larger tables that are usually modeled in a third normal form. So for instance, if you have a CRM and you want to update a customer's address information, the application is only requesting the records, a small amount of records that pertain to that customer's address, such as city, state, address lines, those kind of things. So if you can imagine, those are small, relatively small data sets being returned. Data warehouse workloads are very different in that they are scan-centric, and what that means is sequential reads and writes. And the most important performance metric here is megabytes per second. So if you think of this workload, it is very historical in nature. It is very analytical. Your queries are typically in the form of wanting to analyze different units or transactions that have occurred in history or in the past. So for example, what are my sales, current sales for this month, or what are my month sales? In that scenario, all the transactions for a month need to be aggregated up to the month level and compared one month against another. A single query can return thousands, millions, or even billions of rows of data, all those sales transactions that need to be aggregated up. So in contrast to the many small data sets that are returned with OLTP systems, data warehouse workloads have very large data sets that are returned. And so the appropriate measure there to measure the performance is megabytes per second. In other words, throughput. How much data can I quickly deliver off my disk onto my CPU to be aggregated? In an OLTP system, your data is usually relatively very volatile, meaning you're continually making updates, DML operations, data manipulation operations, updates, inserts, or deletes, such as updating customer information, creating new transactions, those kind of things. And there could be thousands of transactions occurring on an OLTP system at any given moment. Data warehouse workloads are typically very different in that they are relatively non-volatile compared to OLTP systems. They are characterized typically by nightly loads, a batch load process that loads data nightly from the previous day into the data warehouse. And so once that data is loaded, transformed, and in the final tables, data warehouse tables, to be used for our analytical queries, it usually is not updated after that point until the next nightly load process. There are exceptions to this, and I will address those. Things like near real-time data warehousing kind of violate this distinction, but I will address that in later episodes. So for OLTP systems, in terms of indexing, your indexes are very important. And and you can have very complicated schemas related to your indexing to make sure you get the optimal seek performance, because you're seeking individual or a small handful of rows from larger tables. And so being able to specifically tune your indexes and predict your queries, what they will be seeking will greatly improve the performance of your OLTP system. Data warehouse workloads, on the other hand, have a very light indexing strategy. And mostly focused on what are called fact tables. So the indexes for your fact tables, and these are very simple type of index in that you usually have one index per fact column, and that's all. Because of the ad hoc nature of data warehouse queries and analytical queries, it is almost impossible to determine ahead of time the exact characteristics of those queries. Something like clustered index or column store indexes can greatly enhance fact table performance, but in a scan-centric way. So, and I will address those later on. As mentioned before, many indexes are created in OLTP systems to support that optimal seek-centric type workload. And fact tables or data warehouse workloads are index light, meaning they are very straightforward and simple to set up. OLTP workloads have a high concurrency, so a high number of users that are using the system at any point in time, so hundreds, or even thousands of users accessing the application and the underlying data warehouse at any given moment is pretty typical. And so the data needs to be modeled and the hardware needs to be architected in such a way to support that. Data warehouse workloads, however, are typically characterized by low concurrency, meaning remember, these are very large queries that return a large amount of data, and so historical data, and so the more users you have, that can dramatically affect performance, because these users are not returning lots of small data sets, but relatively few very large data sets. And so if you have a requirement to have lots of users for your data warehouse workload, you need to think and very carefully plan for that. So that wraps up the description of the data warehouse workload. Next, I'd like to move into a little bit of architectural kind of considerations here. So what I have displayed on the screen is kind of the typical setup. You have on the bottom, you have right here the storage, and on the bottom you have several servers. Now this storage kind of represents a SAN type layout, meaning that these servers share a common storage device, and so all their data is on this device, the SAN device. The problem with this picture is that your OLTP systems servers and your data warehouse servers are connected to the same storage, but because these workloads are so different, there will inevitably be conflicts between these servers in terms of their workloads. A data warehouse workload, a single query, can return many gigabytes of data, and while that is happening, the I/O components that are responsible for delivering that data from your storage can get overwhelmed. And if that happens, then your application servers will not be able to satisfy their OLTP type queries until the data warehouse query is completed. So that's why in many situations the data warehouse gets its own dedicated storage, because its workload is fundamentally different and can overwhelm very easily the workload of the OLTP system. And again, this is called throughput in many situations, and the key metric here is megabytes per second. If you want to visually think of this, I think of it this way. So both in this picture we have vehicles with wheels, transmissions, those kind of things. So some common components in that sense, but they're all they're both performing very different type workloads. For instance, on the right-hand side, you have a Bugatti, and on the left-hand side, you have a tractor. And they're both using gasoline, they both have gasoline engines, and all those kind of similar components, but it wouldn't be fair to measure these by the same metric. In other words, 0 to 60 time, right? The Bugatti would perform that a lot faster than the vehicle on the left. However, it doesn't mean that the vehicle on the left isn't performing work or isn't being efficient or performing its job well. It just means that there's fundamentally different workloads, and so measuring both of these by the same metric doesn't really make sense. And the same principle applies for measuring OLTP system performance versus data warehouse performance. Okay, and now that we are fundamentally grounded in the difference between a data warehouse and an OLTP workload, now we can start getting specific about how do we best manage this data warehouse workload. And at a very high level, I've kind of categorized all the techniques, procedures, and best practices into 3 main categories here. And this is what I call the data warehouse trinity, meaning that these are 3 fundamental principles that, if followed, act as kind of a synergy, that all 3 exponentially increase the performance of the other if used in concert together. If any one of these 3 are lacking, you'll still get pretty good performance, but it'll always be limited. So, starting at the very top with star schema. Star schema is the appropriate data model for data warehouse type workloads, mainly because it uses centralized fact tables. These fact tables can be optimized for scan-centric operations. Remember, that's fundamental to the data warehouse workload, having it perform well. And then these facts are essentially sliced by or filtered by dimension tables, which are usually much smaller, typically less than 1 million rows. So, and I will do a series of follow-up videos. I'm not going to go into too much detail about the star schema, the dimensional modeling techniques, simply because there's great materials out there, in particular produced by the Kimball Group. They are kind of the standard here, and so I highly recommend reading all their books, but if you only read one of their books, then read the Data Warehouse Toolkit. That will give you a solid foundation for understanding the dimensional model. They also have a series of other books, in particular a Microsoft-oriented book as well that I would highly recommend. The second point here is a balanced architecture. So now this refers to the actual hardware architecture to support a data warehouse workload. And again, there's great materials published out there. Some of the materials in my presentation come from this. There are the fast track reference architectures, and so these are best practice, data warehouse specific best practices published by Microsoft and then its hardware vendors as well. You can use these as guides to constructing or architecting your own hardware solution for a data warehouse. Or you can buy an appliance, which is a pre-built system that has both SQL Server, the software, and the hardware in it. Built into it are best practices, many of the best practices which I cover in this presentation. The last bullet point here, parallel data warehouse, I just want to call this out. This is kind of this is Microsoft's MPP, or Massive Parallel Processing Solution. I will talk more about that in greater detail. I have been working with these type of solutions for over the past 1.5 years, 2 years, and I've been very impressed with this architecture, so I will cover that as well. So with the data model and the hardware architecture, there is also a follow-up thing here, column store indexes. And so this is something that was introduced new in SQL Server 2012 and has been enhanced in SQL Server 2014. These are such a dramatic enhancement that they deserve their own kind of category here. Now you can go to the SQL Server column store index fact. It has lots of great information there, and I will have lots of demonstrations around column store indexes and indexing in general and how that's best applied in a data warehouse scenario. If you do not have SQL Server 2012, then you can use things like page compression and other techniques such as table partitioning applied to both fact tables that don't have column stores and ones that do. So I will cover those techniques, but I consider that all part of column store indexes. So with those three things in mind, even with someone with relatively little experience with data warehousing, if they follow those three things, the end result will be a very good data warehouse, a data warehouse that most likely will meet their needs and perform well, which I hope is the main focus and the emphasis of this, is that you realize that data warehouses are usually described in most scenarios in terms of their size. And while that's important, that's a little like describing a car as having 4 wheels. Of course, you need enough space to hold the data for your data warehouse, but what's important is the performance of that car or the performance of that data warehouse. And so that's where true engineering and architecture comes into play, and that's the whole purpose of this presentation, is to be able to engineer a data warehouse solution from the hardware components all the way to the software and data modeling side of things to get the best performance possible from that, and predictable performance as well. So next, I'm going to dive in a little bit into the hardware side of things. There's so many variations in terms of hardware architectures that could be developed for data warehouse specific workloads that I'm only going to cover one basic scenario, and your hardware architecture probably is very different or might be similar to this, but this is just kind of a basic scenario. So on the left hand side I have the server. So this is the actual server, the SQL Server, running Windows Server as well, and there's SQL Server right there, and you have caches on the SQL Server side of things, the Windows Server thing, and you have CPU cores. So that is where the queries are coming in. So when the queries come in, they're going to hit the SQL Server, and so SQL Server is then responsible for either trying to satisfy that query from cache, or if it doesn't exist in cache, doesn't have all the data in cache already, then SQL Server has to request that data from the disks, from the disk storage where that data resides. And in a data warehouse workload, the fundamental characteristic there in most scenarios is that you can't fit all the data into cache, and so it needs to be queried from disk, because you don't have years or months or quarters worth of sales data transactions just sitting in memory. It's a tremendous amount of it can't fit in memory, so you have to retrieve it from disk. So moving over to the extreme right hand side of things, you have your disk layout here. So you have pairs of disks. These are rated together, let's say in a RAID 1 scenario in this case, and then they're exposed to the operating system in a series of LUNs. Alright, so and your RAID level will vary and things like that, and I'll go into greater detail about those kind of things. So fundamentally, that query then retrieves all the data from its disk, which then makes its way through your storage controllers, through a fiber channel switch, through the HBAs, which are basically just network interface cards specific to fiber, and then onto your server where it can then be aggregated. So making sure that whole process is optimized and is consistent becomes the secret to having a good performing data warehouse. So again, starting on the right hand side of things, here for each enclosure, each big rectangle here that has, in my graphic, 2 LUNs supported by 2 disks apiece, each one of those gets 500 megabytes per second throughput. Each LUN, sorry, gets 500 megabytes per second throughput, and there's 2 in each enclosure, so that gives me a total of 2 gigabytes, roughly 2 gigabytes per second throughput coming out of my whole storage setup: 2 arrays, 2 LUNs, 2 disks per LUN. Again, this is a simplified version. Then you need to ensure that your storage controllers can actually support that 2 gigabytes per second, because if your storage can deliver 2 gigabytes, but your controllers can't efficiently process that 2 gigabytes per second, then you'll never get that throughput all the way to the server. And then, of course, your infrastructure responsible for your switches, in this case a fiber channel switch, needs to be properly set up, and also have the capability of handling that 2 gigabytes per second. Special consideration needs to be dealt with in terms of setting up the interface to the server from the switch as well, to ensure that that 2 gigabytes is also maintained. So each HBA in this case can support 1 gigabyte per second, and if they are multipathed, then they are working in parallel, and so that becomes 2 gigabytes per second. And then, of course, on the core side, you need to make sure you have sufficient performance capabilities of your CPU cores, that in total they are capable of consuming, or in other words, aggregating that data up at a rate of about 2 gigabytes per second. So that's kind of this graphic, and so this is more or less the basic understanding you should have of a data warehouse system. Most data warehouse systems are not constrained on the CPU side. Usually you can buy enough CPU consumption to more than satisfy what is required of your data warehouse. Usually most data warehouses are constrained on the storage side, or somewhere in between. So if any one of these devices, I/O components, in the middle that connects storage to your server doesn't get that 2 gigabytes of throughput that I have in my little example here, then the whole system is slowed down or is constrained by that one. So it's very important to test all these I/O components to make sure they're getting consistent throughput, because otherwise it doesn't really matter how much data you can deliver from disk, or even how much you can consume, because that bottleneck is the constraint on the entire system. So this is what's referred to in fast track reference architecture materials as a balanced system, or in other words, it can consistently deliver, in this case, 2 gigabytes per second all the way to the CPUs and be consumed. Now this is what's referred to as an SMP system, or symmetrical multiprocessing system. I will go into more details about this and other technologies, MPP, Microsoft's Parallel Data Warehouse, later. But just keep in mind that the reason why this is called symmetrical multiprocessing is because the effects of this is if you want to scale this up. So let's say, for example, in a few years that 2 gigabytes of throughput is no longer meeting the business needs in terms of performance, and you need to increase this. Well, what happens is this can become a very complex and costly process, because in essence, in an SMP system, you have to start throwing away the majority of these components and upgrading them, because these components were specifically architected to get a certain throughput. And now when you demand more throughput, the majority of these components have to be thrown away. New components have to be bought, and you have to go through that whole architectural process of testing and ensuring that they get that constant throughput. So that's kind of the scale up approach. So basically it's you throw it away, you buy new stuff that's more powerful. And in many scenarios, you eventually, data warehouse gets to a point where there is no single SMP system that can give it, even the latest greatest SMP systems produced by the hardware vendors no longer meet the performance requirements of the data warehouse. And so then you have to go into what's called a distributed computing or massive parallel processing solution for that. So just keep in mind the upgrade path, because this is a very typical scenario. There's many instances when initially when a data warehouse is bought, it is, let's say, appreciated over 3 to 5 years, and good planning is done, but then something always happens, life happens, and a new business is acquired, a new data source is found, and all of a sudden the performance and the data storage capabilities of the data warehouse are greatly taxed and need to be increased. And so these unexpected things can happen, and unfortunately the only solution is to scale up, is to obsolete that hardware and buy completely new hardware and go through the entire tuning and architectural process that you went through before. So now I'm going to briefly touch on a few things that will help you in this hardware architectural process, and I'll come back to this later in greater detail. So the first and most fundamental step here is to measure the performance in terms of megabytes per second of your storage. Alright, so everything that was on the right hand side of those two graphics. Once you know your capabilities there, you'll have the foundation for performance for your data warehouse solution, because no matter what database engine you use, whether it be SQL Server or any other one, none of those database engines are going to be able to deliver data faster than what your storage subsystem is capable of delivering. So if your storage subsystem is capable of delivering 1 gigabyte per second, and you need to have 2 gigabytes per second data delivered from SQL Server, that's just not going to happen, simply because it is constrained around the hardware. So being able to measure and architect that hardware capability is the foundation for data warehouse performance. And the best tool for doing this is a tool called SQL.io. And what this does, it has a poorly named, but what that essentially does, it has nothing to do with SQL Server, but what it does is just write a test file on your file system, so on Windows Server. And you can do that in many different ways. You can adjust, for instance, the size of the file, the block sizes, whether or not it's reading or writing from the file, sequential or randoms, reads and writes. And so, and of course for data warehouse scenarios, we care about sequential reads and writes. And then outstanding I/O requests or queue depths. That's just some of the parameters available to you to use in SQL.io, and again I'll cover this in greater detail, and it forms the foundation of the performance of your data warehouse. So now I've used this tool many times, and so once you run this tool in many different scenarios and those parameter values I described previously, you're able to chart out the performance of your data warehouse like so. So above I have a chart, I have I/O requests, which is like queue depth, random reads, which we will not pay attention to, sequential reads, random writes, and sequential writes. And I've highlighted kind of the maximums for sequential reads and sequential writes out of this system. So average megabytes per second. Now this chart represents actually hundreds of I/O tests done with SQL.io, aggregated together. So, and what you want to pay particular attention to is the sequential green reads and writes, and the sequential writes. The sequential reads in green, the sequential writes in kind of light blue. And as you can see, both these lines increase up to a certain point and then level off. That is good. That means that you've, in your SQL.io test, maxed out this system, so you know exactly what its performance capabilities are. And depending on the many different hardware configurations and possibilities, the performance will vary across several different scenarios. So I have queue depth on the bottom. And as you can tell from this system, in terms of its sequential reads, it maxes out at about 1500 megabytes per second. So you will never get more than 1500 megabytes per second returned faster than that returned by any query, by a single query. Now if you have concurrency, multiple queries going on, then they have to kind of split that out. So that's your query performance, 1500 megabytes per second. And then your sequential writes, this is on your data loading side of things. So how fast can SQL Server actually load data into your data warehouse? Again, SQL Server will be constrained by the hardware capabilities of the data warehouse. In this case, 1200, about 1200 megabytes. In this case, SQL Server will not be able to write more than 1200 megabytes per second into its database. This is a physical impossibility because it is constrained by hardware. So if your data loads need to occur in a shorter time frame, and this 1200 megabytes per second isn't going to match that, then there's nothing SQL Server can do about that. You need to have different hardware to support that. So again, this gives you the foundation of an existing system. So this is a single system, and the block size here is at 64K, which is kind of the minimum block size. And I'll go more into block sizes later in later videos. So then this graphic represents is kind of the culmination of what I've been discussing. Here I've charted out multiple systems, and this is all reads. So these are just reads, 64 block size, just like the previous one, but under different hardware architectures. So to begin with, this QS data warehouse, Quick Start data warehouse in green represents a fast track. This is just Dell's fast track reference architecture and appliance. So this is an appliance you can buy from Dell, and this is maxed out at about 2 gigabytes per second. That's why I've been using that number. So it gets the highest out of all these. The blue, the DAS, or direct attached storage, this is a direct attached storage solution with solid state devices. So this is solid state device performance with direct attach. And the direct attach is a good solution. However, this particular one wasn't specifically architected for data warehouse workloads, and even though it's SSDs, because it wasn't architected correctly, it gets less than your Quick Start data warehouse, which is just regular spinning disks. This purple line represents a SAN. So SANs, again, are optimized for OLTP workloads and not for data warehouse workloads. So this SAN has a combination of SSDs and regular hard disk drives as well. And this would be what I would refer to as a tier 1 SAN, right? So this is a very expensive SAN, but even though it's very expensive, it gets only slightly more than 1,000 megabytes per second. The blue line is kind of a tier 2 SAN, which is supported by just hard disk drives. Again, because it's OLTP optimized, data warehouse workloads, it doesn't perform very well. And then the bottom red line is my personal laptop. So hopefully that gives you an idea of what different architectures and why having a hardware architecture specifically designed for data warehouse workloads can make a dramatic difference. Because this Quick Start data warehouse is only a small fraction of the cost of let's say these SAN solutions. These SAN solutions, particularly the tier 1, is probably 5 to 6 times more expensive than the Quick Start data warehouse solution, at least. And so making sure that you get the most performance for your cost is very important. And so it's so I hope that can make an impact on how these different architectures perform together, and the importance of properly architecting these.